Hello, you fine bunch of people. We are back at the end of Unit P, working through some little more complex problems here, where all the stuff that we've learned comes together here. So you will see an example like this on an exam, and so you should be able to work through a word problem like this. I'm going to look at questions 12, and then 13 we'll take up in class. I'll also, in this video, do number 14, and then leave number 15 then to take up in class. At the end of this, there's a bunch of problems here that you can work through, and please, please, please do these. These are really important problems to work through. And of course the answers are here. And at the very end here, there's a great dice game. I like dice games because they deal with probabilities. You don't have to know how to play this game, but if you want to take a break, this is really a fun game. And that'll take us to the end of Unit P. Then we'll get into the binomial distribution. So let's back up here then. And we're going to take a look at number 12 first of all. Hit and run crimes are a problem in our town. Last year's figures showed that 20% of all hit and runs were caused by trucks and the rest by cars. Figures also show that in 40% of the cases where trucks were involved, the victim was killed, while in cases where cars were involved, only 10% were killed. Yeesh. How do you do that? What I want you to note here, and this is the way I always start these things off here, is I want you to note that there is 4 types of probabilities that we have been introduced to. The probability of some event A is a marginal probability. And I suppose its complement, of course, not A, is we can include that. I'll put that in brackets. And so that's a complementary. But I'm just going to focus on, if we have marginals, then we know what the complementary event's not A is. But the second most important one here, or the second type that we learned, is a joint probability. And the operative word here is and. So if you can rewrite the sentence or the phrase using the word and, then it means it's a joint probability. Oh, I made a mistake on the one above, didn't I? Anybody catch what the problem was? I wrote it as a conditional probability. Let's rewrite that. I could go back and do the whole tape again, but I'm not going to do that. This is what a joint probability looks like. There we go. So it's got that kind of upside down U here. Then what we've got here is the probability of A or B. This is a union, and the operative word is or. And then finally, we've got a conditional probability. That's shown with the line here. And the operative word is given. So given that B has occurred or will occur, what's the probability that A will occur? So those are the 4 types here. Again, complementary probability is just whatever's left over from the marginal, so we won't include that in future ones here. Now, let's take a look then at setting up a contingency table here. And so the contingency table looks like this. And we've got really 2 dimensions of the problem. So it says here then that a person is either hit by a truck or a car, and then they're either killed or they're not killed, which is the complement of that. All right, let's see what we have here in terms of statements. So last year's figures show that 20% of all hit and the runs were caused by trucks. So 20%. This is a joint probability. No, it is a marginal probability. It's not a joint probability because it is only talking about one dimension of the problem, the type of vehicle. It doesn't mention anything about whether the person is killed or not. So it's got to be in the margin of the table, right there. Actually, I'm going to change that back to black here for the colors. Now, that means when it says the rest are by cars, then that's got to be 80%, which are hit by cars. We could write that down then as another marginal probability, or of course it is the complement of the t. Figures also show that in 40% of the cases where trucks were involved, the victim was killed. This is a given. The given part is where trucks were involved. So this is what we've got. It's like this. Here's the trick. Is what you want to look for is prepositional phrases and subjective clauses. Ooh, you didn't think that you needed English in this particular course, did you? But you actually do. So when you see a word like where trucks were involved, that means given that we're talking trucks. The other word that you'll often see is of. So you'll see that in the preposition. So of the males, or whatever, or in this case, of those who were hit by trucks, 40% were killed. That's another way we could write it. Or of the males, or of those wearing white, or whatever. So the word of, as in a preposition here then, is saying given. All right, so in this particular case then, where trucks were involved is the subjective clause. So given that trucks were involved, we've got that 40% were killed. Now remember that a conditional probability never goes straight into a table. The only thing that goes into the tables are the marginals around the outside and the joint probabilities on the inside. So we have to actually break this down here and use the formula. The probability of k given t is equal to the probability is equal to 40% is equal to the probability of k and t. Sorry. There we go. Of k and t over the probability of t. Now, we know that 20% were hit by trucks. And so that's going to be 40% of 20%, which is 8%. And that goes in here, like that. I suppose if you want to use the symbols and so on, you could say the probability of k and t, k and t is equal to the probability of k given t times the probability of t. So it's going to be 40% of 20% is your 8%. All right, let's change colors now. While in cases where cars were involved, so there's your subjective clause here, where cars were involved, given that they were hit by a car, we have that 10% were killed. That's equal to the probability of k and c over the probability of c. This is going to be equal to 80%. Right? 80% are cars, were hit by cars. So 10% of 80% gives you 0.08. Now these two numbers are the same just out of coincidence here. But what we have here now is everything that we need to fill in the rest of the table. So now we can go here and add up this column, and that comes to 16%. the complement of that. So we have 16% are killed. That means that 84% are not killed. And then for each row, we can say that 0.08 plus 0.12 is 0.2, and then 0.08 plus 0.72 is equal to 0.80. So you've got the full table. All right, now it should be easy to answer these next questions here. So let's take a look here at a question. What is the probability, what proportion of hit and runs resulted in the death of the victim? That's simply equal to the probability of being killed. And if we've set up our contingency table correctly, then that's this guy right here. It's a marginal probability. Last week I talked to a fellow who was a hit and run victim. Let's go to a different color here. Let's go to this one. His injuries have healed nicely. What does that mean? It means he didn't die. So given that he was not killed, what's the probability that he was hit by a car? Again, when you're doing this on an exam, write that down. Probability of C given not K. And then write it out as a formula here. That will help you systematically to get the right answer. And also, it'll help me to mark it. So what this means then is that we're focusing in here on this column, and we're looking at that. So that's going to be 0.72 divided by 0.84. And there's your answer. Now, again, you can leave that in that form. That's the answer. I assume that you can pull out a calculator and figure out what that probability is, but that's close enough for me. Finally, is there a dependency between the type of vehicle involved in the hit and run and whether the victim survives the encounter? Let me show you how I do these things. I make up a little table like this. This is just reproducing what we have above here. So we've got T, C, we've got K, and not K. And then the probabilities that we have are 0.2 and 0.8. So these are just the marginals that I'm putting in. Like that. So I didn't put in any of the inside cells. Now all we do is we are using this here. The probability of A and B, if they're independent, is equal to the probability of A times the probability of B. Or, for instance, for that first cell in the upper left, we have probability of T and K. If they're independent, should be equal to the probability of T times the probability of K. So probability of T is 0.2. Probability of K is 0.16. So it's going to be 0.2 times 0.16 is going to be 0.036. 0.032. How's that? That's better. Okay. 0.032. So all you need to do actually is for any cell, let's take a look at the next one here. You don't have to write this formula down in each case. Just simply take the marginals and multiply them together. So 0.2 times 0.84 is 0.168. Of course, add those together and you'll get 0.032. Add those together, you get 0.20. And then similarly down here, so 0.16 times 0.8 is going to be 0.128, and then 0.672. So now we could take those to about 2 decimal places and so on, but what we have here then is that for the first cell here, what we've got is that this turned out to be 0.032, and that's not equal to what we have above, which is 0.08. In other words, what we've got is more people were killed by trucks than we would expect if they were independent. I just have to let my dog out. Just give me a second here. So I'm comparing the bottom table, which is what we would expect to see if they're independent of each other, to the one above, which we calculated the values for. And what we see then is that it's higher in the T and K that we would expect. So I can go through and do that for each cell, which I've got the numbers here. What we want to do then, in order to describe if there's a relationship between them, is what I like to do is I like to go through and I like to circle the cells where the actuals are higher than the corresponding expected. So I've put those in yellow up there, and now I'm just going to write a statement here and say what this is telling us then is that there is a greater chance of being killed if hit by a truck. Okay, so they are not independent, or you could just simply say that they are dependent. And that's how you would write the relationship. There's a greater chance of being killed if hit by a truck, and obviously then, consequently, you don't have to write this down, but there's a lesser chance of being killed if you're hit by a car. So that's how we would describe the relationship. All right, I'm going to stop this particular one here, and then we're going